So given what we have built up so far, we can actually use these pieces to build a heap from scratch. So we've got, let's see, a set well, we have the heap structure, in this case with 7 nodes, and we filled it in with just random 2-digit numbers, and it's not a heap at the moment. But we can make the heap property be satisfied, and this is the way we're going to do it. We're going to start off at the root, which is node 0, and we're going to say, okay, well, to make this into a heap, well, first magically make this into a heap and make this into a heap. And once we're done, then we can do down heapify on this value and everything will be fine. All right, but how do we build a heap out of this smaller piece? Well, we can do it again recursively. We can say to build a heap rooted at this node, make this into a heap, make this into a heap, and then down heapify. Well, how do we do these guys? Well, the singleton nodes are already heaps. So anything that is a leaf already, we're done. That's our termination condition. So this is a heap. Here, I'll check them off as we go. This is a heap. This is a heap. This is a heap. This is a heap. All right. So now to make this whole thing a heap, we need to do our little swap thing. So 88 gets swapped. This is down heapify. 88 gets swapped with 30 because 30 is the smaller of the children. And now that down heapify is completed, this whole thing's a heap. We need to do this subtree. Again, same trick. These guys are already heaps. To make this into a heap, we have to swap it with the smaller of the children, the 13. Now down heapify finished, so this is a heap. And now we've got just the last little step. To make the whole structure here into a heap, we need to do down heapify on the root node, which means swapping it with the smallest of the children. That's the 13. And continuing recursively, because that's what down heapify does, swapping it with the smallest until we reach the bottom, and that's done. So the whole thing is a heap. We made a heap. Woo! Perhaps even cooler, the running time is quite nice. The time it takes to build a heap out of n elements, well, we build 2 heaps of size n over 2. Then there's a log n step to down heapify. And this is a slightly hard piece to analyze. It's not so hard to figure out that we're essentially running down heapify, which is a log n operation, on each of the nodes sort of as a root. So we know that it's actually big O of n log n. And there's a tighter analysis, which I'm not going to give, that actually shows that this T of n is in big theta of n. So we can actually establish the heap property throughout a tree of n nodes in linear time. That's pretty cool.